So let's talk about series circuits. Essentially, series circuit is more than one load connected in a circuit, but they're connected in series. So what does that mean? Well, ultimately it means the same current goes through all of them. So I've got a great PowerPoint here that I'm going to share with you, and we'll discuss much more about series circuits. The definition of a series circuit was really pinned by Kirchhoff. Kirchhoff was an incredible guy. He did a lot of really cool chemistry stuff and a lot of really awesome science stuff way back, a long time ago, like in the 1800s. What he was doing was he was hooking up circuits in different ways, and he was studying the interaction of the currents and the voltage. And I mean, Ohm's Law had been around for a long time when Kirchhoff was doing all of this. So he used Ohm's Law to prove how circuit voltages and how circuit currents work if you hook up circuits in either series or parallel. Yeah, we will talk about parallel circuits definitely in our next chapter or discussion. So right now, let's just say, hey, Kirchhoff, you're a cool guy. He did a lot of really cool stuff. He was really into light and electromagnetic radiation. But yeah, he seemed to unpack all of these rules about how we apply Ohm's Law depending on if circuits are connected in parallel or in series. So essentially the definition of what's going on this week, what we're going to do is we're going to discuss identifying series circuits, determining the currents and the voltages in series. We're going to apply Ohm's Law, and we're going to see that we're going to apply Ohm's Law a little bit differently in series circuits than we will in parallel circuits. And then we're going to determine the total effect of voltage in series. So essentially what we're going to do is we're going to hook up voltage sources in series and kind of see what happens. Yeah, later again when we do parallel circuits, we're going to hook up voltage sources in parallel, and we'll see it's actually quite different. And of course we're going to apply Kirchhoffs Law. So let's move forward and take a look at what a series circuit is. A series circuit looks like this, or more specifically, this isn't like a whole circuit. This is just a bunch of resistors connected in series. Yeah, I think you're getting it now. You're like, yeah, okay, that makes sense to me. They're all connected in a line. Yeah, okay, well, that makes sense. So essentially what we can see here is we can see the current is traveling through all of the resistors. However they're hooked up, they can be hooked up in all different kinds of funky ways. However you look at it, there's really only one path for the current to go. So one path goes into the circuit, and then the current goes all through all of them, and it comes out. But that, you can look at it this way, every single electron actually ends up going through every single load. So essentially, we've got this resistance formula that's really complicated for series circuits. Yeah, no, not quite a bit. Dude, just add them up. I mean, it's that simple. RT is R1 plus R2 plus R3 plus R4 plus... And ultimately, you can look at this as though, hey, those electrons, or the charge, is having to go through every single one. And actually, as we know, each resistor kind of slows down the charge, or kind of says to the voltage that's pushing it, no, and it's stealing some of that voltage. And we'll see when we get into a little bit deeper that we see the voltage drop increases and increases and increases until finally we're left with nothing. But ultimately, you can look at it this way, in that the charge that's going through has to go through every single one of them, and by the time it gets to the end, it's had to go through all of them. So the resistance it encounters is the total of all of them. There you go. So let's just take a look at this really basic circuit. Here we go with the first kind of basic circuit. And we can essentially just say, okay, so what is the total resistance? Well, we just put the formula together, put in the values, and then write the answer. 3 steps to a formula. Like, that's it, just 3. So now let's take a look at this example in kind of different perspective, in that we're going to use different metric prefixes. And then, so what do we do about that? Well, in this case, we have different metric prefixes. Essentially, what I'm going to highlight in these next 2 slides is the fact that when we have the same metric prefix, let me go back to that other slide. When we have the same metric prefix, I mean, as we know, we can do math with the units. So right here, essentially, there's a couple different ways to do this. I could just put bracket 1 plus 2.2 plus 2.7 bracket kiloohms. That's it. Because you can add kiloohms to kiloohms to kiloohms to kiloohms, but you can't add kiloohms to ohms. Or you can, but when you do it on your calculator, you have to use notation. You have to use engineering notation. Okay, good. Here we go. So in this situation, we've got mega ohms, kiloohms, and kiloohms, and just ohms. What do we do? Dude, write the formula. Fill in the formula. Oh, in this case, what I've done here is I've written the values in engineering notation. This is what you have to type into your calculator. You can type in 0.5 kiloohms if you want, but you've also got to write 0.5 times 10 to the 3. Or in this case, if you wanted to, you could write 19,500 ohms plus 500 ohms. Essentially, that's going to possibly screw you up. Dude, just use the metric prefixes on your calculator. Now, if you really wanted to, you could write this like this. Let me go over here. You could change this to mega. You could change this to kilo. You could change this to kilo, and you could just do that. And you can write your formula that way. But you just have to make sure when you put it in your calculator, you do it like that. Okay, moving forward, we can see we write it down, we fill it in, and then we write the answer. Pretty simple. Again, this next step is the same situation where we've got all of this notation here. Now you've got to put this in when you put it in your calculator. Again, you can write this 2.57 giga ohms, and then you can like, whoa, how many? 9? What is that? Yeah. So, or you can write mega ohms, and you can write it that way. I'm just writing it like this here, so you realize that's how you have to put it in your calculator, or you'll not get it right. Dude, just don't try and put in a bunch of zeros or put in all of those values. Use engineering notation. Okay, I'm letting that go now. I can move forward. Okay, let's go. Let's move forward. Let's take a look at Kirchhoff's voltage law. Essentially, what's going on here, it's really very similar to the resistance formula. It's just the voltage drop across resistor 1 plus the voltage drop across resistor 2 plus the voltage drop across resistor 3 equals the voltage source. Now, I'm going to talk about the concept of voltage drop and another kind of voltage that we call voltage potential. But that's going to be in my second video on voltage dividers. So for now, just believe me here, we have this concept called voltage drop. Essentially, it's the energy that's lost, because we know voltage is energy per charge, right? It's the energy that's lost pushing that charge through a particular resistor. So we can kind of look at Kirchhoff's voltage law like this. The total energy supply coming from the battery that pushes that charge or those electrons through the circuit is lost by the time it gets to the end. Actually, that's per coulomb though, right? So as we push this 1 coulomb, we lose a certain amount of energy across resistor 1. Then we lose some more energy, and actually when we do that, we're actually left with less voltage. And then we lose some more energy across the third one, and by the time that's all done, that equals the actual energy that was put out of the battery in the first place. So the voltage source, whatever it is, if it's 12 volts, we can see that voltage drop happens across all of the 3 resistors. It doesn't always happen evenly. It depends on what the values of those resistors are. Again, we'll take a look at that a little later when we get into the voltage divider. Here we go. So essentially, we can just look at this a couple different ways. We can also see this as the sum of the voltages minus the voltage source is going to equal 0, or the voltage source minus the sum of all of the voltage drops is also going to be 0. Just a different way of looking at that. Okay, here we go. So here's just this great example so we can see, and we've got some different voltages here, because we can see that if we apply this to Kirchhoff's discussion about how resistance is and all of the different resistances in total, we can see that the voltage drop across R1 is huge because the resistance is huge. And then the voltage drop across the last one, R5, is like ridiculously small. Microvolts? Yeah. We can see that the higher voltages are because the resistances are higher, right? And then just adding them all up, just because the formula says so, it's V1. the total voltage drop across the circuit, or the voltage source, is equal to V1 plus V2 plus V3 plus V4. Just write in the formula, fill in the values, and write the answer. Now, just kind of wanted to highlight something a little bit. There are kind of two things that are important to highlight here as far as like the mathematical documentation goes. One is, as we know, we can do the math with the units, and you can put the voltage right outside as long as you put brackets. So let's just take a look at this. I got a bracket and then all of these numbers and then bracket voltage. So that voltage applies to every single term that's in there. So it's 5.14 times 10 to the 3 volts plus 854 volts plus 5.18 volts plus 818.6 times 10 to the minus 3 volts plus 1400 times 10 to the minus 6 volts. There you go. Now, the other thing I wanted to note was I can't actually use metric prefixes in this case. Like that last slide, I said, yeah, you could just say kilo ohms plus mega ohms plus milli ohms and whatever. Just you can write it down. As long as you put it in your calculator properly, you're good. But I just wanted to say metric prefix indicates it's a prefix. It's a prefix to a unit. So I can't actually write 5.14 K plus 584 plus over here 818.6 M milli, right? And then here just micro, because those metric prefixes have to come before units. If I really wanted to write that, I would write, if I wanted to use metric prefixes in here and get rid of this engineering notation, I could do that. I just write VS equals 5.14 kilovolts plus 854 volts plus 5.18 volts plus 818.6 millivolts plus 1400 microvolts. And then I could just do that. And when you put it in your calculator, boom, you're going to end up with some kind of value. There you go. So now I'm going to rewrite that value with the metric prefix, because ultimately, you know, you can write a value down in engineering notation. It's not mathematically correct, but it's just not intuitive. It's good to talk in metric prefixes. So if you have a value and you've calculated on your computer and or your calculator, just write it down in a metric prefix. Okay, there you go. So now what's going on here is I need to tell you guys about current, right? So essentially what's going on with current is that, as we know in our discussion from current in our previous PowerPoint or a previous lecture, we know that there are kind of two kinds of current. There's conventional current and electron flow. I just kind of want to highlight that again in the fact that we've got current running through some kind of circuit, and we know that the electrons actually go from negative to positive, right? But we don't say that. Yeah, okay. We actually say that they go from positive to negative. So John Thomson, J.J. Thomson, what he did back in the 18 something, what did I say here? Oh, it was actually right in the late 1800s. What he did was he kind of looked at these things. He discovered the electron, which is pretty cool, dude. He actually discovered the electron, and he's like, oh no way, dude. The electron is a negative charge, and the electrons are the thing that actually they're moving in the circuit. Those are the things that are moving. And then he's like, oh, Ben kind of got it wrong. Yeah. So he figured that out. But by the time that actually happened, everyone had embraced the idea that Benjamin Franklin came up with. This charge goes from positive to negative, right? So all of our conventions, all of the math, even the symbology behind all of the symbols we use for electronics kind of were drawn as though the current's going from positive to negative. So we just kind of roll with that, and we're just going to actually calculate everything as though it's going to go from positive to negative. We're going to talk that way. Essentially, if we're doing electrical control stuff, current goes from positive to negative, but it doesn't really. Okay, let's move forward. There you go. So essentially, what's going on is I need to discuss the concept of a node. Okay, so a node is just a spot in a circuit, and we name it something. So this is just node, we call it, say, node A. In this case, I've just labeled it as a little blue dot. So we can say that the current into a node in series is the same as the current leaving the node. The reason I'm kind of saying that is ultimately because that type of discussion helps us unpack parallel circuits when we get there. Because nodes in parallel circuits act a little differently. But in this case, in a series circuit, the current going into any point in the circuit is equal to the current leaving that point in the circuit. And I'm just going to call it a node for now. We're actually going to use nodes a lot more when we discuss voltage dividers. There you go. So in this case, I've got, this is actually so cool. This helps us so much solve like puzzles. I've got a bunch of puzzles here that we will be solving in this PowerPoint, where this concept of the current through R1 is the same as the current through R2, is the same as the current through R3, is the same as the total current, will help us solve these puzzles in a really, really cool way. So we can actually call, we can say IR1 equals IT. I could even in a formula write IT instead of where I write IR1, but we just see what happens as we calculate these things. Okay, there you go. So now in a single resistor and in all resistors, we can see that this formula here, so IR is VR over R, which is just the general form of anything. We can see essentially that one of the resistors in a series, you can determine the current using just that one. So I can apply Ohm's law to calculate the current through resistor 2. So in this case, this is easy. I'm using Ohm's law. IR2 equals VR2, the voltage drop across R2, divided by R2. There you go. So now I've just calculated IR2. Guess what? I now know the total circuit current. And this is kind of a little bit trippy. I know this is kind of hard to wrap your head around. Okay, wait. So if Ohm's law tells me that the current through R2 is a very specific value because of Ohm's law, how come the current through R1 or R3 is the same, even though when I use Ohm's law, I'm going to be using different values? It's actually quite eloquent in that they work out because the voltage drop across the other resistors is different because the resistance of each is different, and they kind of balance out and they kind of dance around the current. Like the current's kind of the boss, right? The current says, no, dude, I have to be this amount. So you voltage drop, you have to change a little bit because of that particular resistance. We can also look at that as though the voltage is the boss as well, and the current in the total has to kind of balance out, because actually if I did this calculation, I could say the total resistance and the total voltage drop, which is actually the voltage source, go together into Ohm's law and calculate the total current. So, and that's down here. I can see IT equals VT or VS over RT, right? So that is actually going to give me the exact same current as just finding the current in any one resistor. It's kind of heavy to wrap your head around that. Like I kind of also think it's so cool, but it also kind of like, really? It's almost hard to believe. Because, dude, R2 and R1 have different values. They're different resistances. So how come the current's the same? Because the voltage drop across each is also different and they balance out. Cool. So that's Ohm's law in a series circuit applied. Okay, there you go. So what? Sorry, here we go. Yeah, so I can calculate this and it's going to be the same thing. In this case, I've got my voltage drop across all of these here is 10 volts. And the total resistance across all of these here is 10 ohms, and I've got 1 amp. In this case, my voltage drop across here is 3 volts, and the current, the resistance here is 3 ohms. So I'm also getting 1 amp. Very cool. So that's just an example here. So let's just take a look at this. I can see the current through here is this much. Wherever I look in the circuit, through node A, through node B, through node C, the current is always the same here. And in this case, I'm seeing the resistance is 5.9 times 10 to the 3 ohms, or 5.9 kilo ohms, and I just put this into my formula and I press play. Now, just kind of highlighting a little bit on the math with the units, or the mathematical documentation. Ultimately, if I wrote slash 5.9 times 10 to the 3, and then I just hit enter on my calculator, I would get 18 divided by 5.9, whatever that is, and then I would have to multiply that value times 1,000. And that's not going to be the right value. I have to write 18 divided by bracket 5.9 times 10 to the 3, and then bracket, and then hit enter. But because our calculators are cool, we have these functions in our calculator that we just hit an E, right? So you just write 5.9 E or EE, or maybe there's another symbol there, and then you write the metro prefix and you hit enter. You don't need to use those brackets when you're using the function on your calculator for engineering notation. But if you actually wrote this out exactly like this on your calculator, you'd actually have to do this. And because I'm writing it down mathematically, I have to do that. The other thing that I can do is I can just write 18 volts divided by 5.9 kilo ohms. It's easier to write it that way, but as long as you put it in your calculator properly, you're good to go. There you go. So 3.015 milliamps. Now in this case, what I have is I've also got the same total resistance. It's kind of silly in this particular example to say the total resistance is 5.9 kilo ohms. Well, dude, there's only one resistor. But you know what? What if that resistor was actually made up of several other resistors in series that equaled 5.9 kilo ohms? There you go. So essentially what I'm doing here is I can calculate, if I knew the voltage drop across this, I could calculate the current through this, and I would see that it was this. If I knew the voltage drop across this, I could calculate the current using this resistance and see that it's this. Same with this. Now, the thing that's really cool is, what if I don't know the voltage drop across R1? Well, I know the current through it because I know the total resistance and I know the total voltage drop across all of them, so I can calculate the total current. Well, I know the total current is going to be the current through R1, and it's going to be IR2. It's also going to be IR3. So if I wanted to, I could use Ohm's Law to calculate the voltage drop across R1, R2, and R3. Pretty cool, eh? Here's just another example of looking at this concept one more time, and I can say, look, I've got the voltage drop across this. I've got the resistance of this. I've calculated that it's 1 amp. And there you go. That's pretty simple formulation over here. Now, if I do the same over here, I can say that I've got my voltage drop across this guy and my resistance here. If I put it together in Ohm's Law, I can see that it's 1 amp. Also, if I do the total resistance over the source voltage or the total voltage, we generally call it source voltage, or Vs, then I get the exact same value. So Ohm's Law is actually Kirchhoffs and Ohm's Law put together in series circuits. Is like so eloquent. It's pretty cool. So let's apply Ohm's Law and Kirchhoffs Law to kind of solve the puzzle. Okay, so in this situation, we've got 3 resistors in series. We know the total current is equal to the current through any one of them. Now, I've got here, it says that I've got 1 amp running through R1. That means 1 amp is running through R2 and 1 amp is running through R3. So if I use Ohm's Law and specifically look at just R3, I can apply Ohm's Law using the voltage drop across R3 and the current through R3 to calculate the value of R3. Here, Ohm's Law. I just throw my values in and there I got 40 ohms. Nice and simple and sweet. So let's move forward and solve some more puzzles. In this particular situation, what I have is I've got a circuit and I don't know much about R1. I know its value. R2, I have a little bit more information. I've got my value and I have the voltage drop across R2. R3, I don't know. How do I calculate the voltage drop across R3? Actually, there are lots of different ways that we can do this. But right now, what I'm looking at is I'm thinking, dude, this is really nice and sweet. I've got 2 pieces of information about R2, so I can easily find the third. So I'm going to find the current through R2, which is also going to give me the current through R1 and R3. So that's nice and simple. I'm going to write down IR2 equals VR2 divided by R2. I'm applying Ohm's Law specifically to my R2. I'm using all the values that I know about R2 using Ohm's Law, and I'm finding out the current through R2 is 5 milliamps. Now I know the current through R3 because it's the same. So now I can use Ohm's Law and I can say V equals IR and I can write IR3 and I know it's 5 milliamps and I can write 3.7 kilo ohms. Again, I'm not writing 3.7 times 10 to the 3 ohms on here. I'm just writing kilo ohms. Get used to just writing that down, but when you put it in your calculator, you've got to use engineering notation. Okay, good. Oh, wow. So nice. 18.5 volts. Perfect. Now I've got another option. Like I said, there are lots of options here. Let's just take a look at this one. This second option is a little bit extra work, but we'll delve into it anyway because it's just good practice to look at different ways to solve these things. In this case, we're actually going to use the formula that, sorry, we're going to use the IR2 that we've already solved for, and then we'll apply it to Ohm's law, and then we'll apply it to Kirchhoffs law. Okay, here we go. So I'm using IR2 to find VR1. Okay, that's cool. So I'm just going to use Ohm's law here. I'm going to apply all the values for R1, specifically using Ohm's law, and I'm going to find out that the voltage drop across R1 is 50.5 volts. Okay, now I'm going to use, so that's actually a second step, because to do this I have to calculate R1 in the first place, or R2, or R3. But I calculate R2 and then I use it as R1. Okay, good. So now my next step is to then take Kirchhoff's voltage law and say the voltage source equals voltage across R1 plus R2 plus R3. Rearrange that formula to say VR3 equals Vs minus VR1 minus VR2. Because I now have VR1, I can put that in and I end up with 18.5 volts. And we can see over here it's the same value. So, and there are probably other ways to do this. Wrap your head around this and try this different ways. Maybe try it. Let me actually let's analyze a different way. Do you know what? I could get the total resistance. I could say RT is R1 plus R2 plus R3, and then I could calculate IT. Okay. Now I then could say IT equals IR3, and then from there I have the current going through R3, and I have the resistance of R3, and then I can use Ohm's law to find the voltage drop across R3. There's probably another way to do it too. I'm thinking of one using power, but we won't get into that right now because there are other slides that are about using Ohm's law and power and Kirchhoff's laws all together. Okay, moving forward, power in a circuit. Oh, here we go. Yeah, this is what's going on here. Power is actually a really powerful thing. Power is so cool because when we get into parallel circuits, there's like this magical aspect of power that kind of transcends Kirchhoff's laws. Really? Yeah, we won't talk about that now. Wait till we get parallel circuits. Okay, good. So what is the value of the voltage source? Okay, so we're going to use our understanding of the power formula. We're going to find out some values. We're going to apply Ohm's law and Kirchhoff's law together to solve this puzzle. Here we go. So essentially, I've got the power of the motor. Okay, so I want to find the voltage source here. So if I knew the voltage drop across R1 and the voltage drop across R2, I could just calculate that. But let me just see. If I knew the power of the motor, I mean, and could I calculate the voltage of this and the amperage? And how do I do this? What's going on? Well, I know the current. That's really cool. If I knew the current and I know the power, well, P is V times R. So it's pretty simple to calculate the voltage drop across the motor, knowing the current and the power. So I've just done that. I've said the voltage drop across the motor is the power of the motor divided by the current through the motor. And I know the current through the motor is 1 amp. I put in my values. Oh, I just lied to you. It says 2 amps. You know what? This circuit is wrong. Pretend that says 2 amps. Okay, see that number, how it says 2 right there? Yeah, let's move forward. There 2 amps, 5 volts. There you go. So now, in this case, I'm going to find the voltage drop across R2, knowing the current, R1. The voltage drop across R1 using the current through R1 and the value of R1. And now I'm going to use Kirchhoff's voltage law, and I'm going to just add the two together and to get Vs. Isn't that so perfect and awesome, other than the fact that I don't know how to type it here. So yeah, just see that number 2 right there? Yeah, that's what's going on. Okay, good. Another example, like very, very similar example with the exact same circuit. But in this case, I know the voltage drop across R1, and I know the power through the motor, and I am looking for Vs again. So in this case, I need to calculate the current. I'm going to calculate the current through R1. And in this case, I know the current through R1 is also going to be the current through the motor. And now I'm going to find the voltage drop across the motor using the power formula again to find the voltage drop across the motor. So voltage drop across the motor is power of the motor divided by current through the motor. And that's 10 watts because it's labeled as 10 watts divided by 2 amps because I've calculated that up here. And that's 5 volts. Okay, good. Now I'm going to use Kirchhoff's voltage law for a series circuit. And I'm just going to add them all up and I'm going to find the source voltage. Okay. Wow, same example again? Yeah. So we've just got some different parameters here. I know the power of my, by the way, all of these values are the same. I'm just kind of putting in different things. We're solving the same puzzle from different angles. Okay, good. So I've got my the power of resistor 1, which is 10 watts. I got the power of the motor, which is 10 watts. I have the resistance of R1. So what do I do? Well, I've got to calculate the current somehow. Now, if If you remember when we discussed power, there are actually 4 different formulas for power. One I'm going to take and kind of throw out the window a little bit, and that has to do with energy per unit time, because we don't really have time in this formula, neither do we have energy in this circuit, so we just kind of toss that out. We know there are 3 other different kinds of formulas for power. Power is voltage times current, that's one of them. The second one is power is voltage squared divided by resistance. And the other is power is I squared multiplied by R. So power is I squared times R. So we have these 3 really powerful formulas for power that we can use. So in this case, what I'm doing is I'm using P equals I squared R, and I'm using that to solve the current through R1. Well, if I know the current through R1, I know the current through the motor. I don't know the resistance of the motor, but I could probably, get that out somehow using some other formula here. So in this case, what I'm doing is I'm using this formula here. It's actually the same formula up here, and I'm saying the resistance of the motor is going to be the power of the motor divided by the current through the motor squared. So I'm writing it down, I write it down, and I fill in the values. By the way, guys, I really want to highlight this. If you just write a 2 here, by the way, when you do your motor control assignment, a lot of people are going to leave these brackets out, and they're going to lose marks because it's not mathematically correct. Did I get a little upset? Yeah, guys, just be mathematically. Mathematical documentation is so crucial. Here we go. So, and it also helps you understand what's going on with the math and with the unit. So in this case, we know that the unit is actually going to be amp squared. Really, there are units that are amp squared? Yeah, there are. I mean, it's just math with the unit. So in this case, but it's also 4 amps squared. So if I were to just write the 2 here above the amps, I'm dividing 10 by 2, getting 5. So my unit is going to be correct. It's watts per amp squared, which is actually an ohm. It's weird. Yeah, a watt per amp squared is an ohm. But in this case, I'm going to get 5 ohms. But that's wrong. We're supposed to get 2.5 ohms. Do you see how the brackets are important? Because that squared, this squared applies to the 2 as well as the unit. Again, some students also write just 2 squared amps, but that's wrong because then your final unit, you're getting the right value because 10 divided by 2 squared is 2.5, but then you're getting watts per amp. I don't know what a watts per amp is. I don't know. It's nothing, or I don't think it's anything. But a watts per amp squared is actually an ohm. Pretty cool. Okay, good. So with that, I can now use Ohm's Law and the total resistance to find AS. Because I know the total resistance. In this case, I didn't even show the calculation for the total resistance. Because if I know the total resistance, or the resistance of R1 is 2.5 ohms, and the resistance of the motor is 2.5 ohms, it's just 5 ohms. So there you go. I didn't even show it because it's just so simple. There you go. So, and that's what's going on, and it's 10 volts. Oh, there you go. So in this case, it was 10 volts. In this case, it was 10 volts. In this case, it was 10 volts. Same thing. I'm just looking at all of this from different angles. There you go. So now let's discuss putting voltage sources in series. Yeah, so you know this is like if you have a battery, if you have a bunch of batteries in a flashlight, you've all put batteries in flashlights before, and you know actually something weird happens when you put one of them backwards. Either the thing doesn't work. Actually, if you only have 2 batteries in a flashlight and you put one in backwards, it doesn't work. If you put 3 in a flashlight and you put one backwards, the voltage is actually going to be a third of all the voltage. Even though you've only put one of them backwards, the voltage ends up to be only a third. Oh, it's really weird, but we'll see the math for this. So there's a formula for this, and it's pretty simple. It's just the total voltage source is voltage 1 plus voltage 2 plus voltage 3 plus voltage 4 plus, and on and on and on, just like that. So it's really simple. Although it gets a little tricky if you don't watch what you're doing. I'll show you that in an example. Just give me a sec here. So in this case, for a practical example, we're figuring out what the total voltage is applied to the light bulb in this flashlight, and we know that each one of these is 1.5 volts, and we put them together, and there you go, it's 4.5 volts, nice and easy and simple. Okay, good. So let's just take a look at an example here where we've got a bunch of these loads put together. So there's this and this and this and this and this. So we're going to assume that each one of these is 10 volts, okay? Nice and simple. So this guy and this guy, oh, dude, really? Look at these two. The polarity of these are backwards. So if these were cells that were put into a flashlight, really long flashlight, one of them would be backwards. Let's just continue to see if any others are backwards. So this is one way, that's another way, that's another way, that's another way. Well, what do I do? Well, dude, write it all down like this. Okay, so I'm just writing the voltage on the side. I'm not totally getting rid of units as much as I can. I can do the math with the units. I'm just putting units, like I'm putting brackets around everything, and I'm just putting the voltage on the outside. Okay, good. Here we go. So relative to how I'm looking at these guys, I'm either going to call this positive or this positive. In this case, I'm calling this positive, that positive, that positive, that positive. Ooh, that's a negative, that's a positive. So that's a negative, that's a negative, in that they're reversed. Take a look at that. It's reversed. So in this case, I'm just going to write minus 10, plus 10, plus 10, plus 10, plus 10, minus 10, plus 10. If I wanted to, I can get rid of those brackets and just write minus 10, plus, 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 minus, plus. So in the end, it's 30 volts. There you go. So it's important that you kind of wrap your head around that. Now, listen, like I said earlier, if there are 3 AA batteries in a flashlight and you put one of them in backwards, does that mean that's 1.5 volts less? Right? It's just 3 volts now instead of 4.5? Actually, the answer is no. Those two, the one that you put in backwards, cancels out the one beside it. Those two just pretty much come out of the formula and go poof. They go zero. Their voltage is zero. Their total voltage between 2 batteries put together backwards is 0. So actually, you're only left with 1 battery that's running that flashlight. So you got to kind of watch that when you're doing the math here, because in this case, I've got 1, 2, 3, 4, 5, 6, 7. Okay, I've got 7. So if these were all connected properly, it would be 70 volts. Okay, good. 2 of them are hooked up backwards. So does that mean I only have 50 volts now? Oh no, it's actually 30. Really? Yeah. Because those 2 backwards ones, they cancel out the one beside it. So these 2 are useless. This guy and this guy, they cancel each other out. So, and so does this one and this one. So I'm only left with 1, 2, 3 that are actually giving me forward voltage. There you go. So just be mindful of that and be careful, because on the midterm exam, there's a question just like this and some of them are backwards. Now what I want to do is I want to jump into power. Yeah, like I said earlier, like power's like magical, but kind of when we get into parallel circuits and then when we get into series parallel circuits, it's pretty cool. Actually, power kind of transcends Kirchhoffs laws. Yeah, we just forget about Kirchhoff. He's not in the picture anymore. Power transcends Kirchhoffs laws, but I mean, it's also really cool and simple. Dude, power, this is where we bring back that joules per unit time, that use of energy per unit time. Now, this can really help us wrap around why the total power in a circuit is the power of R1 plus the power of R2 plus the power of R3 plus the power of R4, going on like that. Because the energy dissipated, or the energy being used in any load, whatever it is, it's a motor, it's doing some work, it's spinning something, or it's a heater, or it's a light and it's producing light and heat, whatever it is, there's energy being used across every single load. In this case, I've just got 3 resistors and they're just creating heat. That's all they're doing. Okay, so they're dissipating energy. So the total dissipation of all of the energy divided by the total time that the energy is being used for is the total power. Okay, so how do I find out the total time? Well, it's just time. I just use a stopwatch or something, right? How do I look at the total energy? Well, it's obviously the energy put out of R1, how much heat is generated there, plus the heat that's generated in R2, plus the heat that's generated in R3. So the total energy is just the sum of all of the energies that are used in the circuit. And that's so cool, because whether it's a series circuit or a series parallel circuit or a series or just a parallel circuit, it's still just energy being used. So the total energy being used divided by how much time you use it for is the total power. In this case, we can kind of apply that in math, just using the power, just saying power 1 plus power 2 plus power 3 equals the total power. And that's what's going on here. That can help us do a lot of really cool things here. This is just another example where we're calculating the value of the motor, okay? Now, I've got different options here. This is a step-by-step process. In this case, I'm going to find, using the total power concept, I'm going to say, oh, if I know the total power here is 20 watts, again, this is the exact same example as we were using before, but we're unpacking it with the total power concept. Okay, here we go. So I know the total power is 20 watts. I mean, it says so here. And I know the power here is 10. Oh, so I can easily calculate the power through the motor. And I can just say the motor power is the total power minus the power through R1. And I put my values in, and then I write my answer. And my motor power is 10 watts. Easy, good. So now I can find IT. And then I can find Vm. So in this case, I'm going to find the total current, which is also going to be the current through R1 and the current through the motor. But I'm just going to find the total current because I know the total power. And actually, in this case, know the total source voltage because it's written on the formula here. I mean, in the circuit. So I'm going to find IT, and I'm just going to write IT is PT divided by ST, and I'm going to put in my values, and I'm going to see that it is 2 amps. Okay, good. Now what I'm going to do is I'm going to say that I now know the current through the motor, which is 2 amps because it's IT, and I'm just going to write this formula here. V of the motor is the power of the motor divided by the current through the motor, so it's 10 watts times divided by 2 amps, and that's 5 volts. And the motor voltage has always been 5 volts, and the current's always been 2 amps. So it looks like all of these things are coming out right. Now, there's a third way to do this, and I wanted to highlight this one because, again, we've got some proper mathematical documentation in here, and it's just the use of the other power formula that we haven't touched yet, which is P is V squared divided by R. So in this case, what I'm going to do is I'm going to find the motor voltage, the voltage drop across the motor by using the power is V squared over R. In this case, the resistance of the motor is going to be the voltage of the source, the total resistance of the total circuit is going to be the voltage of the total circuit in the power of the total circuit, the voltage divided by the power of the total circuit. So in this case, I'm finding the total resistance. In this case, by the way, take a look at this. I'm doing 10 volts bracket squared because volt squared divided by watt is actually an ohm. Volt squared divided by a watt is an ohm, but just a volt divided by an ohm? Volt divided by a watt is not an ohm, but a volt squared divided by a watt is an ohm. There you go. So now I've got 100 divided by 20, which is 5. Again, if I only put this squared on this V, I'd end up with 10 divided by 20, which is 0.5, which is not right. There you go. So, and then from there, I can find the resistance of the motor using the total resistance formula. The total resistance is the resistance plus 1 plus the resistance plus 2. So I can say the resistance of the motor is the total resistance, which I've just calculated, minus the resistance of R1, and now I know the resistance of the motor. Okay, so I calculated the power of the motor in the very beginning, right? It was the first thing I did, and I know that. I know the resistance of the motor, because I just calculated that through a 2-step process. And then from there, I can use the formula P equals V squared divided by R. I can rearrange that formula, and I can put everything together, and I can get the motor is 5 volts. So what we've done here so far is we've taken Kirchhoffs laws, Ohm's law, and the power formula to solve more puzzles in circuits. And it's up to you to decide how to use these things. And how do you know? Dude, practice. Just write a bunch of these down, practice. Go through the worksheets, go through the homework, practice this stuff, and then you'll be like, oh, look at that. There's a nice quick shortcut here. Because, for example, this particular example, I did this in 2 different ways. One is I used this here, I calculated that, and then I did this. So knowing the power of this, I did a 2-step process here, but knowing the power of this, I did a 3-step process of here to find the same thing. So it's a matter of practice to figure out, how many steps to do, and it's like a cool puzzle. Just play with it like it's a puzzle. So what I want to do next is I want to talk about open circuits. I want to talk about voltage across open circuits. And I think we got to pause on this because, again, this question's on the exam. Let me explain why this is true, okay? Then I think it'll make sense to you. What's the voltage here? I mean, what's that voltage meter read? What does it read? Actually reads the source voltage. It's actually going to read 30 volts. Yeah, really? doesn't make any sense. But that's not across the voltage source. Well, get this. We know it's really all about kind of Ohm's law in this case. We know that the reason there are voltage drops, right? This is kind of the concept between voltage potential and voltage drop, something we'll delve in much deeper into when we get into our next PowerPoint slide, which is about different kinds of voltages and using the voltage divider formula. In this case, what I want to say is a voltage drop exists because there's energy used pushing charge, through a load. Okay, so there's a voltage drop that exists when energy is used pushing charge through a load. Okay, how much charge is being pushed through this load here, R1? 0. So how much voltage drop exists across R1? 0. So what's the voltage potential at the other side of R1? Vs. So that's seen on that meter. So in essentially what's going on, because there's no voltage drop here, Vs is seen right there by the meter. Pretty cool. So again, there's a question on the exam that's like this, and the answer is whatever the Vs is. Good. So now let's talk about shorts. A short in a circuit. What does that mean? When you've heard that like, oh, there's a short circuit. What does that mean? Well, what's going on is that for some reason, something's gone funky in the circuit. It could be that a wire fell down in a circuit and it touched a particular spot in the circuit. It could be that someone was in there with tools or something and they kind of bridged two areas of a circuit or a screwdriver or something and it shorted out a particular component. What happens when we shorted a particular component is essentially we're kind of bridging around that component and the component just kind of leaves. It's like the resistance of that component no longer is part of the formula. Not at all. So if we take a look at this, if I put a fuse in here, 500 milliamp fuse. So if there's more than 500 milliamps of current going through that fuse, it will blow. It'll blow. Okay, good. So let's actually see if this fuse will blow. We're going to use Kirchhoffs laws and Ohm's laws to figure this out. Okay, good. So in this case, what's the total resistance? Well, the total resistance is 10 plus 10, 20 ohms. The total resistance is 20 ohms. Now, before the short, if that short wasn't there, the total resistance would be 120 ohms. Okay, so let's just kind of just do the math here. Okay, so wait, what's the current? My voltage source is 12 divided by 120 ohms. So the current is going to be 100 milliamps. Okay, so before the short, the current's 100 milliamps. So I've got a 500 milliamp fuse in there. It's never even going to get warm. It's not even ever going to get stressed. But now that I've got this short in here, the total resistance of this circuit is 20 ohms. So I'm going to go 12 divided by 20, and that's going to be 600 milliamps. Uh-oh. Yeah, the fuse is going to blow. So it's actually, yeah, shorts are not a good thing. But hey, maybe fuses are a really good thing. Yeah, dude. So we need to put fuses into circuits because things go wrong with circuits and we get shorts. And one of the other things that actually is a good example of a short is a motor. If you stress a motor out too much, it will actually overload and something will break inside, it'll get hot, and then there can be a short in the motor, and all of a sudden the motor is just not even there. It's shorted out. So the resistance of the motor is not part of the circuit anymore, and the fuse blows. Yeah, fuses are pretty awesome things. Okay, good. So a short circuit here, we can just see this. In this case, I've got 1 amp flowing through here, so the total resistance here divided by the source voltage is going to be 1 amp. And in this case here, what I'm doing is my resistance is changed because that's no longer part of it, and that's no longer part of it. So my current goes up considerably. Good 3.5 times up because I've shorted something out. Short circuits are a real problem. So in summary, what we've discussed so far is the current is the same at any spot along the way in a circuit, in a series circuit. And the other is that essentially the total resistance between any 2 points is the sum of those resistors, plus the total resistance of a whole circuit is the sum of all of those. Voltage sources in series just add up. That's pretty simple. Now, Kirchhoffs Law, or specifically Kirchhoffs voltage law for a series circuit. You kind of have to say all of that because Kirchhoffs voltage law for a parallel circuit is different. So I'm going to say Kirchhoffs voltage law for a series circuit is the sum of all the voltage drops around a single closed loop in a circuit is equal to the total voltage in that loop. Yeah, it's just that Vs equals VR1 plus VR2 plus VR3 plus VR4. There you go. So now we also have this kind of last little bit here where we look at another way of looking at Kirchhoff's voltage law and say the algebraic sum of all the voltages, both sources and drops, around a closed path is 0. Yeah, so it's just like, 0 equals Vs minus VR1 plus VR2 plus VR3 plus VR4. And we can also put source voltages in there. That kind of helps us, this whole kind of everything equals 0 thing. The voltage drops in a circuit are always opposed in polarity to the total source voltage. It's kind of important in that because essentially what's going on is that a voltage drop across a resistor is a voltage drop. So it's subtracting voltage. Yeah, so Vs is R1 subtracted R1 plus, or we could say 0 equals Vs minus R1 minus R2 minus R3 minus R4 VR1 plus minus, I'll say that again. 0 equals Vs minus VR1 minus VR2 minus VR3 minus VR4. So essentially all of those voltage drops are taking away voltage from the voltage source. Now, current out of the negative side of a source and into the positive side. Well, we know that that's actually true, but we don't say it that way. It's not actually, that's electron flow, but we actually use it the other way around. There you go. So everything you need to know moving forward about series circuits is done. Like, they don't actually get more complicated than this. It's just a matter of applying these rules and practicing. Okay, bye.